Okay, today I'd like to do just a short intro discussion about increments and differentials. In Calc 1, hopefully you studied these and you saw that the true rate of change in a function given a small change in the x value was quite often very difficult to calculate, whereas the differential was pretty simple to calculate usually if you could differentiate the function. But I want to talk today just about the notation. So we're going to draw a couple of pictures, and we just want to focus on the notation involved. So first of all, we'll draw a little diagram here. Doesn't have to be fancy, no need for it to be fancy. And what we have is just some sort of function here. And we pick an x value. Now that's going to generate a y value, which we're going to call f of x. Now we're going to move over a little bit to a new x value, which is going to be x plus delta x. And that's going to generate a new y value over here, which we're going to call f of x plus delta x. Now delta x usually is going to be very, very small. But you see this distance right here, is going to be our delta x. And delta x is an increment. Now that's going to generate a difference in the y values. And that's going to be the increment delta y. And delta y is going to be the true change in y given a small change in x. So actually delta x is going to be a small change in x, and then delta y is going to be the change in y corresponding to this small change in x. And it's going to be defined as x plus delta x minus f of x. And as you saw in Calc 1, this can really be difficult to find. So we want to look at the idea of differentials. Now I could put this all on the same page and on the same graph. I would put it on the same page, but I could put it on the same graph, but it gets really cluttered. So let's just draw the same diagram down here again. Just any old function here. And we'll pick again x value. There's the point on the curve corresponding to that x value. And we want to move over by an amount delta x. Okay, now in this case it's the same distance as in the first picture. But we're now going to call that distance the differential dx. So delta x is defined to be exactly that same distance, which is dx. Okay, but this time we're going to call it a differential in this picture. Now, instead of looking at the distance, delta y, which is the true change in y, given a small change in x, what we want to do is go back here and look at the tangent line to the curve. We'll draw that in red. So there's the line tangent to the curve. And the distance here from the line tangent to the curve down to the original y value, that's going to be our differential dy. That's the differential dy. Now, you learned in Calc 1 that if delta x is very small, the differential dy is a really good approximation to the true change in y, delta y. Delta y is the true change in y given a small change in x. Whereas the differential dy is just the distance from the tangent line down to the original y value, here, f of x. But now here's where the discussion of the notation comes in. The slope of the line tangent is f prime evaluated at this x value right here. But this is just a straight line. The tangent line is just a straight line. And therefore, that slope of that red line is going to be the change in y, which is the differential dy, divided by the change in x, which is the differential dx. Now, the cool thing is, or maybe the confusing thing is, this was the notation, the Leibniz notation for the derivative. And this is a notation that your book commonly uses, because now this is much easier to typeset and print. But this was Leibniz notation for the derivative. Isaac Newton's notation for the first derivative was an x dot. So we've got this notation, and up until, I guess, this moment, if you haven't thought about it, this was seen as a set of directions. You want to differentiate whatever y is with respect to the variable x. But now we see in this setting, this is really a fraction. The numerator is this distance, dy, and the denominator is this length, dx. So that means if we want to, and here's the whole point of this discussion, if we want to, we may rewrite this as dy is equal to f prime of x dx. And see, there's no magic going on. There's no hocus pocus. It's just a consequence of this differential discussion. Now, where are we going to use this? Well, this doesn't make sense, but I'm going to put up here a typical problem we're going to be doing later on in the course, and I want to show you what's going to happen. So down the road, just not too long, we're going to be given a problem like 1 over x plus 9 to the 10th power dx. And the way we're going to approach this problem, we're going to let the variable u equal x plus 9. And then we're going to take the derivative of u with respect to x. In this case, this is just 1. But then what we want to do is rewrite this as du is equal to dx, treating this as differentials. So see, this ability right here is going to show up as this kind of thing in a problem down the road. And unless you're aware of how this notation works, this isn't going to make any sense, because if you're still in the point of view that this is the notation for the derivative, then this doesn't make any sense. When we go, we'll let u equal x plus 9, and then du is equal to dx, that's going to make no sense at all, and you're not going to follow then what we do next. This then becomes the integral of 1 over u to the 10th du, and then we'll continue to work the problem. So the thing is, this little short video, this little notation, is this just to get us familiar with the fact that this is the notation for the derivative, but we can also view this, when we choose to, as a quotient of differentials and do this kind of step right here. So this was the point of the video. Well, I hope that helps a little. Well, I thought since I had all the gears set up, I would go ahead and do a little discussion about the fundamental theorem of calculus part 2. And the generalization of the fundamental theorem of calculus part 2 that we looked at in class. And this will give you a chance to go back over this discussion and maybe look at it at your own speed, and because it is quite interesting. We've got the chain rule going on, and we also have the fact that we're looking at the notation in terms of differentials. And you can see the previous video that I've done for that short little discussion. So this is kind of a cool topic, and we've got this initial setup Well, our coordinate system is the ty axis, and we're looking at some function f of t, and we've are interested in coming up with a representation for that interval right there. And from our previous discussion with the Riemann sums, we see that this right here represents that shaded area. Now, if you change x as you move x to the right or left, you get different areas. So when you change x, that results in a new value for the area. That is the exact definition of a function. And since this is calculus class, what we want to do is come up with some sort of idea of what that derivative is going to be. Now, we're going to use this notation in the discussion. Okay? Now, what we did in class was this, and this isn't exactly the thing to do. It's not exactly correct, but students seem to understand this. If we use the fundamental theorem of calculus part 1 here, then we're going to have, in the brackets, we're going to have some antiderivative evaluated at the upper limit, minus then the antiderivative evaluated at the lower limit. But you see, a is some number. That means f of a is some number. And therefore, when we differentiate, that drops out because the derivative of that number is 0. Well, capital F is any antiderivative of this function, the integrand. So when we differentiate this capital F, we have to get back the integrand. That's what it means to be an antiderivative. So this ends up just being f of x. So it is really just a simple idea that when this is an x, in the integrand, wherever you have a t, you're going to plug in an x, and that's the solution. So let's do just a really quick example here. Suppose you want to differentiate the function from 1 to x, e to the t over sine squared t dt. Well, the solution is just e to the x over sine squared x. Now, what's kind of mystifying is it doesn't seem like you've done anything. But remember, the derivative is the instantaneous rate of change of this function. So it turns out the instantaneous rate of change of the function that originates when we slide this x back and forth, the instantaneous rate of change is just the y value of that coordinate. That's a wild idea, and that's going to take a little while to get your head around that. But that's all we simply do. We don't find an antiderivative. We don't do anything. We just simply plug x in for the variable t. And the common questions I get in class are, well, what happens to the 1? Well, see, this would be f of 1 here, capital F of 1, which is just a number. And therefore, when we differentiate, it drops out to 0. Now, the question is, can we do better than this? Well, the answer is, of course, we can always do better. So what happens here if we want to look at the situation where we want to find the derivative of this, where this is some function other than x? See, that's going to be the real question. So what are we going to get? Oh, that's hard to see. What are we going to get here when this is some function, say capital N of x? What happens when how do we proceed when this is some function other than just an x? Well, here's what we do. We take and we're going to try to make somehow this problem look like this formal definition here. we want to try to make this given problem look like this. Well, right here's where the difference is. Everything else in the problem's the same. Right here's where the difference is. So I'm going to try to do this. I'm going to let u equal that n of x. Now, there's nothing special about the letter u. You can use whatever letter you wish. But as soon as I do this, then that transforms the problem into the integral from a to u f of t dt. Well, that's better, but see, the problem is this is the differential dx, and this is the letter u. So what we need to do here is the chain rule. We come down here and play a little game. We're going to play a little game here. So we're going to get and take the differential, the derivative with respect to x, and we're going to rewrite this as the derivative with respect to u times the derivative of u with respect to x. So see, if we want to differentiate this function n, we first have to go through the variable u. So to find the derivative of n with respect to x, we have to take the derivative of u and then differentiate u with respect to x. It's just a chain rule. Then what we're going to do, we're going to take this and plug right there, except we're going to split them up. So let's write equals here, and then come down here and we'll do this. We'll have the derivative with respect to x, integral from a to u, f of t dt. And then we're going to write this. We're going to put this one first. This is going to be the derivative with respect to u, integral from a to u, f of t dt. Now I'm going to impose some brackets around this, and then I'm going to put this term outside here. Okay, now the thing to note is that what's inside the brackets is exactly what we did up here if you change the x's to u's. So this inside the brackets is simply going to be f evaluated at u. And then out here we have a du dx. Well, you might say, well, how did that help? Well, look, right here I've got u equals n of x. And now if I differentiate both sides, I get du is equal to n prime of x. Okay? So where I've got the du dx, I can put the derivative n prime of x. So if we go back and put everything as it was written originally, we want the derivative with respect to x of the integral from a to some function n of x, f of t dt. Well, this says it's going to be f evaluated at n of x, and that's just going to be a composite function, times then du dx, which is n prime of x. Now, if you compare this, let's put a star by it, to this, it is simply just a generalization of what we started with. Okay, so we'll call this page 1. So that's what we've got so far. So let's look at page 2 now. So we've got our generalized here fundamental theorem of calculus part 2. So our formula at the moment is the derivative with respect to x, the integral a, and the upper limit is some function f of t dt. Okay, what we do is we take the function, the integrand f, and we plug in whatever n of x is, and then we multiply, and this is where the chain rule comes in. We multiply by the derivative of that function n of x. So let's look at a couple of examples here. If we want to find the derivative with respect to x of 1 to cosine x, and the integrand is t squared plus t plus 9 to the 4th dt. So to differentiate this, what we're going to do is everywhere we have a t, we're going to plug in cosine x. Okay, so this is going to be cosine x quantity squared plus cosine x plus 9, all of that to the 4th power. And now by the chain rule, we come up here and differentiate the cosine function and get minus sine x. That's all there is to it. That's pretty straightforward. Let's do another little example. Suppose we want to differentiate the function 2 to the power of, the upper limit is x e to the x. And what we've got here is going to be t to the 4th over sine t dt. Okay, suppose that's what we've got. Well, we're going to plug in x e to the x everywhere we have a t. So this is going to be equal to x e to the x to the 4th, divided then by the sine of x e to the x. And now by the chain rule, when I invoke the chain rule, I always put the chain rule part in square brackets. I do that because whenever I miss a problem, I invariably will miss the problem at the chain rule part. So makes it easier for me to check. What I need to now do is differentiate x e to the x. Well, x e to the x is a product, so I have to use the product rule. So it'll be the first, which is x, times the derivative of e to the x, which is just e to the x, plus the second, e to the x, times then the derivative of x, which is 1. And that's my answer. Pretty straightforward. So this is pretty good. This is a nice generalization of Fundamental Theorem of Calculus Part 2. But now we can do better. We can do a little better. Suppose you're presented with this situation. Suppose you have some function m of x here and a number here. Well, we're going to invoke a property. We know one of our properties is that we may switch the order of the limits of integration, but we have to pay a tax of a minus sign. A negative sign is introduced. So we're going to do that. We're going to make this minus the derivative with respect to x, integral from a to m of x, f of t dt. And now, this is just exactly what our definition is that we just created. So this is going to be a minus f of m of x times m prime of x. Okay, invoking this generalization that we did earlier. Well, I hope you can see where this is going to go, because this is going to be a cool little deal here. Watch this. We are now able to fully generalize the Fundamental Theorem of Calculus Part 2. That is, what if we want to differentiate this integral? What do we do if both the upper and lower limit are functions? There's no numbers anywhere in the limits of integration. Well, we're going to invoke a property of the integral. Now watch. I'm going to use the property which says, I'm going to use this property. I'm going to sneak it in right down here. The integral from a to b f of x dx is equal to the integral from a to c f of x dx plus the integral from c to b f of x dx. I'm going to use that guy right there. I'm going to use that property right there. So I'm going to write this as the integral from m of x to a plus then the integral from a to n of x See that? I'm just going to use this property right here. And that gives me this. Now, we can distribute the differential through. And that's going to give us this. Just looks absolutely beautiful on the paper. That is really pretty. Now look at what we've got here. We've already done everything on the page. This is what's in this step right here. This is what's in this step right here. So this is going to be minus f evaluated at m of x times m prime of x by the chain rule. And then this is going to be f of n of x times n prime of x. Okay? So let's get a new page and write this down, because it truly is pretty. Page 3. So what we have a new rule. If we want to differentiate, and this is going to be a complete generalization of the fundamental theorem of calculus part 2. So if we're presented with this situation, what we do is we take the upper limit and plug in for t. That's going to give us a composite function. This is going to be f evaluated at n of x times then the derivative of that function, n of x, minus then the function, the integral, whatever the function is, plug in the function m of x, and then multiply by its derivative. Oh, that's just pretty. That is so cool. Let's look at an example. Suppose we want to find the derivative. And let's say downstairs we have sine x. The lower limit is sine x. And the upper limit is e to the x squared. And then let's say in this problem that the integrand is t to the 4th plus 1. Okay? Okay, here's what we do. This is going to equal. We're going to take the upper limit and plug in for t. So that's going to give us a e to the x squared to the 4th plus 1 square root. And now by the chain rule, I have to take the derivative of e to the x squared. Well, remember, the derivative of e to any power is e to that power. And now by the chain rule, we just cover the e up. And the derivative of the exponent is just going to be 2x. Minus then square root. Now, where we've got the t, we're going to put sine x. So this is going to be sine x to the 4th plus 1, right? Times now, by the chain rule, I'm going to differentiate sine x to get cosine x. So that's very, very cool. This is going to be the formula that we want to use. And I'm going to write it again because I think it is absolutely gorgeous. It is just plain beautiful. All right, so there's a complete generalization of the second part of the fundamental theorem of calculus. Now let me state at the end of the video here, what does the second part of the fundamental theorem of calculus tell you? Well, the first part of the fundamental theorem of calculus tells you how the definite integral and the indefinite integral are related. Remember, a definite integral is just a number. The indefinite integral, when you evaluate it, is a function, and that shows the relationship between those two. What the second part of the fundamental theorem of calculus really says, and it's hard to see it with all this notation, it says that differentiation And integration are opposite operations. Just like addition and subtraction are inverse operations, multiplication, division are inverse operations. Integration and differentiation are opposite or inverse. Maybe inverse is a better word. Operations. Cool. Fun stuff. Hope it helps a little. Thanks.